Good morning. We are now going to introduce full-on proofs, and at this point, you're going to go through a process which in your notebooks you're always going to have to fill out in this form so that we can, number one, see that you have good fundamentals in place, and number two, if you get stuck, we know where you had something missing. Even you can put down, I just don't know what I'm supposed to put for number 4. So the steps are the following. After, I believe that first you have to believe it. I have that as a later step here. These steps were developed by students, and for some reason they wanted to do this first. And the reason they came up with was they didn't know what to write down. So keep that in mind, but let's try first to do the 6th step first, so that you first believe what you're trying to prove. But after that, the next step is to write your statement into what we call a conditional statement or if-then format. The next step is to graft out the words after the if and before the then. This is your hypothesis and what you know. This is what you're allowed to use and manipulate. The third thing is to write down clearly what you have to show. This is a step that I used to miss in the past, but it's very important because if you don't know what you're supposed to really try to show, if you don't keep that goal in mind, then you can get off track very quickly. So those are the words after the then, and the adult word for that is called the conclusion. Then you expand what it is what you have to show in symbols or in some kind of way that you can get your hands on, so you know exactly what you have to show in a way that you can see clearly. Now, here I have number 4, to expand what you know, write out the definitions, try to use symbols and expressions that you can manipulate, and you have the same here for number 5. Write out the definitions. There's more on your proof sheet. There's theorems that are equivalent to what you're trying to show. You want to have them all listed because if you arrive at any one of them, you're done. Same for what you know. There's theorems that are equivalent to what you know. Those are things that you can use as well. There's conclusions from your know, that if you know this, then the following is true. Everything you want up, that way you have all the puzzle pieces laid out. Why students would like to skip this often, as I did, is because they feel that this is a waste of time. But it's as if you're putting a puzzle together, and these are your pieces, and if some of the pieces are in another room, you'll never know if they fit or not. Okay, and 6 is really should be a preamble. Test out your problem by choosing some examples. Try to find out why this works or doesn't work. All right, we're going to use this to prove that if n belongs to z, then n cubed minus n is even. Write your statement in if-then format. That's already done. What do I know? Well, those are the words right after the if and before the then. All I know is it's an integer. That's not much. I have to show n cubed minus n is even. Those are the words after the then. I pull it. What does that mean? Oh, well, for number 2, what is it that I can expand on? Nothing really. N is an integer. So there's nothing I can think of. So I'm going to leave that blank for now. How do I expand what I have to show? Well, I told you that anytime you have it's like a word here, like even, and it isn't in some kind of format that you can manipulate, go to your book as a reference and look for somewhere within there where they explain it. On page 85, they define what it means for n cubed minus n to be even. It's not hanging out in a box somewhere. It's a part of a proof. So I did have to scour a little bit. N cubed minus n is even means that n cubed minus n is 2 times a for some integer a. I just used exactly the word. In the book on page 85, they have x is even means x is 2 times a. So I just borrowed what they wrote, and I'm using exactly what they wrote. This is in fact true, that, right, if you think about it, that any even integer can be expressed as, you can factor out a 2. It's 2 times something. So what this means, this is what I have to show. And I have to show there exists an integer a blah, blah, blah. Therefore, my last line is going to be n cubed minus n is 2 times a, where a is, and I have to fill in the blank with something. So whenever there's a there exists, my proof must show, here it is. So I should be able to fill in this blank at the end of my proof. Now I have a problem because I'm trying to prove that n cubed minus n, I'm trying to start out with n as an integer, and I have nothing. I'm not really sure what to do with my hands. N as an integer doesn't give me anywhere to start. So if you have nothing, absolutely nothing to start out with, try to see if you can break out whatever they gave you as the no into cases where you have something to work with. Well, an integer is either even or odd. So that means that all of the integers can be either, if I pick it out, it's going to be either even or odd. Why would I want to think about this? Well, if it's even, I've got something to work with. I've got a formula. We just pulled that out. N is 2a for some a. Well, I just used a in my show, so that's a big no-no. Don't recycle letters. So I'm going to call it b. This is a huge thing to remember. And I have this little Dr. Seuss thing. No, Pat, no. Don't reuse a letter, because if you reuse a letter, sometimes you get to what you have to show and you don't realize that you're at your show because you've abused that letter. So we've already used a to kind of build out what we will have to show. Don't reuse it. I'm going to call that 2 times b instead of 2 times a. Odd means that n is 2 times r plus 1 for some integer r. And I just looked in the book on page 86. They have the definition of what odd means. Again, it's within a proof. It's not on a box somewhere, but that's the definition. So I'm going to first start with the first case. Even means that n is 2 times b for some b and z. I need to show n cubed minus n is even. Or n cubed minus n is 2 times a for in some integer a. So I need to start with n cubed minus n. I sub in my no. Instead of n, I'm going to put 2 times b everywhere I saw n. And I factor. I'm going to factor that 2 times b out. We've been doing that since we were little kids. And this is why I say you have to know what your end goal is. Your end goal is to end up here, 2 times something. So I'm just going to pull out the 2 and leave everything behind. Don't just keep factoring. I know what I'm supposed, that's where I have to keep that goal in mind. Well, there's my a. 2 times something. Let a be that something that's left over. A is an integer. And I can regraft my final statement, which I knew I had to write. Therefore, n cubed minus n is 2 times a. Where a is, I can fill in the blank, this thing right here. And so n cubed minus n is even. Case 2, that's the other case. That's n is odd. Odd means n is 2 times r plus 1 for some r. I'm going to do the same thing I did before, and I'm going to go through this a little bit more quickly. I'm going to factor, and you can factor whatever way you want. It doesn't matter how you decompose it. You can expand things out. I use difference of squares here. I considered this one thing and this another thing squared, and I did difference of squares. And then I noticed that I get a 2 out of this middle term right here. There's my 2. I'm just going to pull that 2 out in front because I remember very clearly that I'm supposed to get 2 times a mess at the very end. And there's my mess sitting here, right here. I don't care how messy it is, with a parenthesis missing right there. So that gives me 2 times a, where that's the mess that I just call all the rest of that stuff a. And I'm able to rewrite my closing statement again and fill in the blank with a equal this thing. So therefore n cubed minus n is even. My closing statement is that all cases have been exhausted, and in all cases I arrived at n cubed minus n even. So I proved that if n is any integer, then n cubed minus n is even. Done. I particularly do not like case proofs because it's just a lot of writing. Some people that I've worked with like case proofs because they know that the final goal can be done. In some ways that's true. I end at the arrived goal, but I'm highly irritated from the writing. So I'm not a fan of case by case proofs, and I'll try to find ways to avoid it. But that's just a personal preference.